We are here with Erwin Staal from the Netherlands. He is software engineer and DevOps consultant. Erwin, how are you today?
I'm fine, thank you. How are you?
Very good, very good. It's my first time on such conference here. I was wondering to ask you a question. I have seen a lot of your speeches, we can say so, on YouTube. Is it your first time on this kind of live conference as we are here now?
No, it's actually not. I've done a few this year already since the coronavirus hit.
Okay.
So yeah.
Okay, so we have a guy with a lot of experience here. And while we are having Erwin's presentation, I would like to encourage every one of you. Could you please write the questions that you might have in the comment side? I read all the questions. I read everything. If you're having problems, that's what we do. I read everything. And hi. So, Erwin, let's start and let's rock this stage. You're on air, and I'm ready to hear your presentation.
All right, cool. Thank you. So thanks everyone. Thanks for joining my session here at Build Stuff this year. It's actually my first time at this conference. Doing it remotely this time. So for the next 40 minutes or so, we're going to talk about architecting for DevOps and continuous delivery. So the question I'm going to try to answer to you is, how do we architect our systems in such a way that we enable continuous delivery of value to our end users? That's the ultimate goal. So my name is Erwin Staal, and I'm an Azure Architect DevOps consultant, and I work for a company called 4.net, which does consultancy and training, etc. In all these stuff basically on the Microsoft technology stack. So that's Azure, that's .net, whatever. So let's get a bit into continuous delivery first. So Jez Humble came up with this definition over 10 years ago, and he's the author of still the continuous delivery book out there. And he says that continuous delivery is the ability to get changes into production or into the hands of our users safely and quickly in a sustainable way. And there's two things in the definition that I find interesting. First of all, is that he talks about changes, not only being code changes, but also being configuration, bug fixes. It could be database changes, whatever, doesn't matter. Anything that you need to get into production. And he also talks about getting it into the hands of our users. So there's not really any value to getting your changes into a test environment or an acceptance environment. We need to get that change into production to make our users actually use the new features. And that's obviously also where we actually make money on the stuff we build. So it's important to get it there quickly. Right, so when I talk to people about DevOps and continuous delivery, now people still tell me that they think that it's either a decision between going really fast and breaking stuff all the time, or going really slowly and therefore be safe. But already in 2018, actually, the State of DevOps report showed that that's not true. The high performance in terms of continuous delivery are actually much better in getting stuff into production than the low performance. So, for example, they get their stuff much more quicker into production. They get new IDs much quicker into production. They actually also make less mistakes while doing that. And if they do happen to make a mistake, then they are able to recover from that much quicker than the low performance. So we can actually go fast and be safe and stable at the same time. So when Jez Humble talks about continuous delivery, he explains that basically that continuous delivery only really has two rules. That doesn't mean actually that continuous delivery is easy, it's not. But the two rules are that software development is always, your software on trunk, on your mainline, should always be in a deployable state. And that should be our highest priority. That enhances quality, and that will make sure that we can always deploy whenever we need to. The second thing is that everyone should be checking into trunk, into your mainline on a daily basis. And when I talk about specifically that rule with developers, then that's the one that I often find hard to do. It needs a mind shift to go from working in isolation for weeks or even months to breaking up their work in such small parts that they can merge that on a daily basis. They say that they feel like it takes them longer to deliver something. There's a bit more overhead in what they need to do to deliver their code. And although that's true, we actually don't really care about how quick a developer can get his work done. We care about how quickly can we get that change into production. And that means that we need to review that code, we need to run all our tests, we need to do performance testing, etc., and eventually we need to deploy that to the production environment. So we actually care about how quickly can we do that whole process instead of just getting dev complete. And doing that whole process is much simpler while having small changes compared to doing the same thing with very large changes. And if anything then happens to go wrong in that process, it's far easier to fix that with small changes than it is with large changes. But it does also mean that we need continuous integration in place. We need to have automatic builds in place, and we need to have a very comprehensive set of automated unit tests in place that can tell us something about the change we make. We need quick feedback on the change that was made. So continuous delivery is basically has 4 foundations, of which these are the first 3. So first, configuration management. You all probably agree with me that if you want to do these kind of things, deploying into production on a daily basis, we need to automate as much as we can. We should really make sure that there's no manual stuff there anymore. So that means that we need to create scripts, etc., to do the whole process, to do the testing, to do the building, to do the infrastructure creation, database migrations, whatever. We need to automate the whole process. And we then store whatever we need to do that into source control. That allow us to always go back in time, pick up a specific version and redeploy that, so we get reproducibility. We also get traceability from it. We know who changed what and when and why. And it also gives us benefits like auditability, and we can even use that to do disaster recovery, because all is in source control and we can always go back to that. We already talked a bit about continuous integration, which is the second foundation. So we need this, whenever someone makes a change, we need an automatic build to be triggered, and we need this comprehensive set of unit tests to be run very quickly to give us fast feedback on the change we're making and how that integrates with changes of our colleagues. And third, we need continuous testing. You can imagine that if you want to deploy your stuff into production multiple times a day, or if you want to push your stuff to production whenever you want, that there's very little room for manual testing. So we need to automate and do continuous testing all the time. Another benefit of automating all that testing is that our testers, our QA engineers, actually get time to do the more complex stuff. Regression testing is something that a computer is very good at. So let's use a computer to do that. And let's have people do the complex stuff. So the fourth foundation here in continuous delivery is about the deployment pipeline. And the idea behind the pipeline is that every change we make results in a build, and that every build is a potential releasable candidate that we could put on production. And the deployment pipeline is here to tell us the quality of the particular build and to let us know if the release candidate is actually unreleasable. And in this deployment pipeline, we optimize for speed on the left. So on the left, we do the checks that we can do very quickly to get fast feedback on our change. So typical things you find on the left is the build of your application and the run of all the unit tests. That should be a fast thing. And then the further we get to the left, the more comprehensive the feedback that we get from the pipeline, but also the longer it takes to get that feedback. So that's where you typically find stuff like UI tests or performance testing or things like that. So the deployment pipeline is here to tell us the quality and the state of our potential releasable shippable increment. And it's basically there to tell us if it's releasable or not. So back to architecture. These are the entities we often talk about when we talk about architecture. We actually create a proper architecture, we build a proper architecture, design it to be able to validate these entities. So the scalability, for example, flexibility, maintainability, security, all that stuff. All those things, that's why we actually talk about architecture and build a proper architecture. There's actually two out of these that are a bit more important in terms of continuous delivery. So the first one is testability. And when talking about testability, we first could talk about things like the solid principles and stuff like clean code. Writing your code in such a way that is easily testable with unit tests, for example. And we also need to talk about being able to run your entire application, your entire stack on your development machine. It runs on my machine as a developer should actually mean something. And if you can't do that because you need to reach out to a third-party system or whatever, then you should probably create test doubles for that. If those aren't in place, or you can't do that because there's a too tight coupling to be able to do that, then you probably have an architectural problem there that you might want to address. The second one is deployability. And deployability means that we can actually do low-risk automated deployments with just the push of a single button. So if it still takes you a few hours to do a release, and you still need to do that in the evening hours or even in the weekend, that probably means that you have some kind of architectural problem right there, which prevents you from deploying whenever you want, even on a Friday, for example. So when I talk to people on how do we then create a system that satisfies both testability and deployability, how do we get that done? Then, especially enterprise, etc., they think they need to move to microservices first. And although we don't necessarily need microservices to do that, the idea they have behind it is that they need to split up their monolith, their service, into smaller pieces. And what we're actually then doing there is a very old pattern in software engineering, which is decomposition of systems. Splitting up our stuff into components to make it easier to handle. So Martin's founder's definition of a component is that it is a unit of software that is independently replaceable and upgradable. So a component could, for example, be a library in your monolithic application, as long as it's replaceable and upgradable. So you will probably use a lot of interfaces to make that happen. But if we put an API layer in front of that library, then we would probably be talking about a microservice. And it doesn't really matter here. So these components do have a few advantages. For one of them being that it's easier to build, deploy, and test them. Since they're smaller, well-written, it's easier to get them built, test, and deploy. It makes it also easier to maintain your entire system, because using components and componentizing your application landscape means you're probably using a lot of interfaces, etc., which means you are doing better encapsulation and lower coupling. So that's a good thing. You will be able to change the inner workings of a component, whether it be an API, a microservice, whether it be a library, doesn't matter. You will be able to change the internals without the outside world needing to know about it and need to change anything. Components could also enable collaboration. And what I mean by that is that we could assign a team to one or two of these components, for example. And that would mean that each team, within the team, you would see detailed communication about the component. High bandwidth detailed communication. And that's fine, since that's just a few people talking with each other on those details. But from the outside world, we would be talking about the component on the API level. So we don't need that much communication to agree with each other what needs to be done and how we can talk to each other. So that's another benefit that we could achieve here by using components and really doing that well. So if you then start building microservice architectures, then what you're actually doing is designing a distributed system. And that means that your system is running on different network components which means that they are going to communicate with each other over the network. They're going to send messages to each other, reach out to each other. And I found this quote by Leslie Lampert. He's a software engineer, and he describes that the distributed system is one that prevents you from working because of the failure of a machine that you never actually heard of. That sure as hell happened to me, and it sure happens when you push your applications to a public cloud. You don't actually really know anymore what's underneath there, and that's a good thing. But it also comes with a lot of complexity. Because, for example, you might hit network latency, which is throwing you timeouts. There might be system failures, hardware that just fails in the public cloud. Complete availability zones or even complete data centers might go down. So you need to work your way, your architectural way around that, because none of the public cloud providers out there, for example, gives you 100% service level agreement on almost any of their services. There are a few services on Azure, for example, on which you can get 100% SLA, but that's either pretty hard to do, pretty hard to maintain, and pretty expensive. So talking about it a bit more, Eric Brewers came in the late 90s actually already with the CAT theorem, and he said that we can never at a single point in time provide more than 2 out of these 3 guarantees. So availability is all about, is your system capable of always returning a non-error answer to a particular request in a timely manner. Consistency is then about, is your system able to respond with the same data all the time? Or would it give you a different set of data if you would request that from Western Europe instead of the United States? Partition tolerance then is about, is your system able to handle hardware failure, for example? So what happens if one of your nodes in your cluster goes down? Is your system capable of still running whenever that happens? So when you deploy your stuff again to the public cloud, then you don't really get to pick partition tolerance. You know stuff is going to fail there. There's no 100% SLA on anything, basically. So you need to work your way around that. You need to architect your system around stuff like that. So let's stay on the microservice track for a while. If you still think it's a good idea to do that, then here's a few things that you should probably architect your way around. So the beauty of microservices is that we could, if you do it right, get an independently deployable unit. But I've also seen teams build microservice architectures and then still having to deploy those 20 microservices at once. When that happens, you've done it wrong. That's not how that stuff should work. There should be independent deployable services. Otherwise, you just could have been building a monolithic application, looking at it from a continuous delivery perspective. It might help you to use cluster infrastructure, so stuff like Kubernetes or Service Fabric. That would at least allow you to have a single deployment model that works for whatever you're going to deploy, and also might save you a bit of infrastructure maintenance, since you probably just need a team to manage the Kubernetes stuff there, and the rest of the teams could probably just use it and deploy their stuff onto it. It doesn't mean that Kubernetes or whatever is actually easy. It's quite hard to get right, even in the public clouds these days. So another thing is that when you go through microservice architecture, you need to be aware of the fact that you should not be breaking your downstream services. So if any service is calling into you, you need to make sure that that works all the time. That means that you cannot make breaking changes to your APIs, for example, and you need to do API versioning to get that right. Since you probably also want to be up 100% of the time these days, we need to get a deployment way of deployment to actually be able to do that. So there's blue-green deployments, for example, rolling deployments, Canary deployments. So the Canary one I'm going to show you later on in a demo. So let's dive a bit deeper into what a blue-green deployment is and what it could do for you. So in the blue-green deployment, we have 2 identical infrastructure stacks in our production environment. And currently our users are going to one of them, and on that particular stack is version 1 of my application being deployed. And when I have a new version 2, I deploy it on the second infrastructure I have. And when I have that warmed up, etc., I'm just going to switch the traffic and load balancer to point to that new version. and then that's exposed to my users. The beauty is that I can always quite easily go back to version 1 if anything did go wrong, because that's still there on the other set of infrastructure. So that's a way of how we can do zero downtime, safe deployments there. As you should be making sure that you don't break downstream, you probably also want to build stuff in to make sure that a failure in a downstream system doesn't impact you too much. So that means that you would probably want to introduce things like the circuit break and the retry pattern to work around that. So the circuit breaker pattern means that if service A is calling service B, but service B is responding with errors all the time, then we open up that circuit breaker and simply don't call that service B anymore for a while. We just give the error back to the user straight away without calling service B. That allows service B to kind of recover from what was going wrong without being DDoSed all the time by the other systems. And then after a few seconds, for example, we try to see if service B is alive again and let one request through. If that succeeds, all the traffic is allowed to go to service B again. If it doesn't, we keep throwing the error to the user right away. So that saves us, could save service B is live. So another thing we could do, especially in a cloud environment, is add the retry patterns to handle especially the transient errors, the errors that might not work right now, so timeouts, for example, but might work whenever we do a second call. We could use, in .NET at least, a package called Poly to make that very easy for us. But we need to be aware that the time between calls to another system, you probably want to make that an exponential backoff, meaning that between each and every call you do, there's a bit more time before you do the next call. That allows the downstream system again to recover from whatever it was suffering from and be able to give you an answer. So last thing I want to mention here is that if you go for the microservice approach, you also want to be looking at monitoring at a very early stage, because monitoring in a microservices environment is much more complex compared to a simpler monolithic environment. It's much harder to figure out which of the components is actually causing your slowness, or which of the components is actually throwing your errors in the UI, for example. So on the other side of things, we still have the monoliths. And if you look at it from a continuous delivery perspective, a monolith could be perfectly fine. There's very large organizations out there that still run their production stuff and still make a lot of money out of monolithic applications. That could work pretty well as long as you have continuous integration at scale. I mean, that would mean code changes to a monolithic repo all the time, and you need your continuous integration really needs to be up a certain level to be able to do that. But it doesn't really matter where on the line between a monolith and the microservices you are in terms of continuous delivery. You could do it wherever you are on that line, as long as you play with the pros and cons and the trade-offs of the particular position you find yourself in. What's probably more important is that you know and realize that architectures should evolve. You're not going to build a prototype and build that prototype as if it's need to handle 1 million users at the same time. You're going to optimize for time to market here first. So that's also why Martin Fowler wrote a blog post on monolith first, in which he basically says that you should always start with a monolithic architecture and then slowly move to a microservice one if you really need to. We're optimizing here for speed again, time to market, and playing with the complexity that comes with that. So he came up with this nice graph over here in which he explains that the productivity you will get from building a monolith is at first in your project going to be much higher than what you will get with a microservice, because simply a microservice architecture is much more complex to build. But you might, in time, find yourself in a position where the productivity in your monolith goes down, and you might actually want to move over to a microservice architecture. But you might also could also find yourself in a project where you never actually reach that point, because if you do monoliths right, there's nothing wrong with that either. So This is actually a tweet from 2015 already, and I found it quite funny. And I once in a while go to the Visual Studio Code Marketplace to see if there's an extension that could actually do that for me. But I checked yesterday, and still in 2020, there's no Architect Clippy extension to Visual Studio Code. So we still need to do that migration ourselves. Luckily, there's a few helpful patterns here that we can use. And there's quite a few nice books on that subject as well. Sam Newman, for example, wrote a very nice book on how to move from monoliths to microservices and how you work with the data, etc. But this is one of them, the triangular application pattern. What you actually do is you place some indirection layer, a dispatcher, on top of the monolith, and then you're able to get pieces out of your monolith, move them into a microservice, and then your dispatcher is responsible for making sure that requests go in the right direction. So your customers, the callers of your API, don't actually need to know anything about what's happening under the hood, and you're capable of making the change. But there's far more patterns that could be useful to you. So please dive into that kind of stuff when you are thinking about making the move. All right, so architecting for continuous delivery and DevOps isn't just about code and the architecture. It's also about designing a proper deployment process. So I'm going to show you a few examples on that as well. So the deployment pipeline starts for most of us here at the pull request. That's where you ask your colleagues to review the changes you make. And you do that before merging your change into the master branch. And although I do prefer pair programming, pull requests still come in handy in terms of a review, but also because we can do all sorts of additional checks there before we merge the stuff into our mainline. So for example, a build has been triggered here. So my application has been compiled and all the unit tests that we talked about earlier have been run. So I cannot merge anything into the master branch before that actually succeeds. So that's a good thing. But we can also do here in this specific tool, but that can be done in others as well, is we can integrate with other third-party systems to do, for example, scanning of our code. So what I've been using here is a tool called Sonar Cloud. And Sonar Cloud can do a static code analysis of your changes. So that means that it can tell you something about the code coverage you have in terms of unit tests. It can tell you something about code duplication. But it can also tell you that you are trying to introduce a vulnerability into your code. And that's what happened here at this particular pull request. So here I was trying to use an MD5 crypto service provider, which is a C# thing to do hashing with MD5, and try to hash a particular password. And as you hopefully all know, MD5 has been for years not the most optimal way to do password hashing. So Sonar Cloud tells me about it, and I can actually click there and go into a bit more detail to see why and what are the proper alternatives to do better then. So the pull request phase is here to put some protection in place for me before merging my changes into the master branch. And after that happened, it's time to deploy my change into, start deploying that into production environments, etc. You first start deploying that to a test environment. And the first steps in this pipeline that I use here, these two are there to create my infrastructure. So we can also do infrastructure creation within deployment pipelines and automate that whole stuff. This is going to create some infrastructure on the Azure cloud, and it's using ARM templates. But you could also be using Terraforms or Pulumi or any other tool to infrastructure as code, doesn't really matter. And here I did it in the same deployment as where I'm also going to be deploying my application. But that's because this is a demo project. In real life projects, you probably want to split the two because the infrastructure pipeline and your code pipeline probably have a different lifecycle. So having a different pipeline for the two is probably a good choice. But the steps over here do create some infrastructure for me in Azure in an automated fashion. And that will also ensure that all my environments are going to be identical. So we don't have any configuration drift anymore between my test and production environment. They're going to be identical because I'm using infrastructure as code. The third step here is deploying my database changes. So again, deployment pipelines aren't only about deploying your code. That's where you might start. But you could also very well be deploying your database changes here in the pipeline. That again means that before you deploy the database change onto production, you've already been testing that a few times on different environments and saw how that goes. That does require obviously a production-like database, also in terms of size. I've seen timeouts happening on the production database migrations, which didn't happen on the test database because it was much, much smaller. So they need to be kind of identical there in size as well. And we then also get the logging that comes from the migrations here in the pipeline, so it's also traceable and auditable as well. And last but not least, there's the deployment step of the application. And this time I'm deploying my application into an Azure web app on the Azure cloud. But it could obviously be anything. So when that has been done, it's probably time to run some additional tests. We already talked about unit tests in the build pipeline, but you're probably going to need some additional testing. And doing that against the test environment might be a very good option. Then, if that all succeeded, it's time to start deploying our change into our production environment. And here, as promised, I'm going to show you an example of a Canary deployment. So what we're going to do here is that we're going to deploy our change to a staging environment first. That's a production-like environment to which there's none traffic at the moment. So we're going to deploy a change there, do some warm-up, and then we're going to send 10% of our production traffic into that staging environment. So the other 90% is still using the old version, 10% is using the new version on my staging environment. And then, before we move into the next phase, the 40% phase, I'm using something called a deployment gate here in Azure Pipelines. And the deployment gate here is that the deployment will reach out to my Azure monitor and see if any alerts went off by making this change. So an alert could be a rise in the number of exceptions of the CPU going up, for example, or the system getting slow. And if none of those alerts were fired, then we're moving on to the next stage where 40% of my production traffic is going to be sent to my staging environment. Whenever that succeeds, the same deployment gate is in place again. We're going to check the errors, etc. And if all still good, we're going to swap the version into production and make all the traffic go to the new version there. So that's pretty cool, a pretty easy to configure, safe way to do deployment into production. So here in this particular system on Azure, that's being done by setting a cookie on the user's request on first entrance. And that will dictate where that particular user is being sent. So this is my demo application for today. It's a very simple MVC application. Doesn't really do that much. But what I want to show here is that you can actually play around with that cookie to influence where you want to go as a user. So I could do this over here, use the query string parameter to tell it where I want to go. So I could do this, say I want to go to staging, and then you actually see the version number change here. So although I'm still using the same URL, I'm now actually using the staging environment. So I could introduce a button on my website, which allows people to use the staging environment if they like, do some testing for me, etc. Before we push that completely into production. So that's pretty cool stuff there. And that's available on other systems as well. So there is actually one thing with this approach, and that is that it's still a kind of all or nothing thing. It's kind of random which users are being sent to my staging environment and to my production environment. It depends on the cookie that the load balancer will give you. We don't really have any further control over that. And it would be great if we would have that. So that's where feature flags actually come in. And you can see feature flags as switches, if statements in your code. that simply turn features on and off. So that might turn on a new feature, or it might turn on a fix for a bug, for example. But what we're actually doing here with feature flags is that we're making a separation between deployment and an actual release, meaning that we could be deploying our code to production 10 times a day to do configuration changes, maybe push a bug fix, but it doesn't mean that we are releasing any new feature to our clients. That's being done by enabling a particular feature. And that feature could come, the value of the feature flag could come from a database or configuration, or as I'm doing here, from a separate feature flag API. And the power here lies in the fact that we could actually base the value of the feature flag on, for example, is this user that logs in part of a particular group? So we could have a group of users that we allow onto the system a bit before the rest of the users. And then this group of users can give us feedback on the change we're making. And that's really handy because we can give the change to them even before it's actually done. So it's at 75%. And then we can ask them for feedback, implement that feedback, and deliver a better feature when we actually deploy that into the production environment at the end. So that really gives you more power over the features you're deploying, and also allows you to hide stuff that you are merging continuously into your master branch from being visible and usable on your production environment right away. So I think we actually have a few minutes left. That's cool because then we can dive in a bit deeper on the testing phase here. We already talked about unit testing in the build phase at the beginning of the deployment pipeline, and also mentioned UI tests quickly when I showed you my pipeline. But there's a bit more to it there. So I always use this testing period by Martin Fowler to explain, to make it a bit more clear. So what we're seeing here is that Martin Fowler explains that you should probably try to get the most coverage, the most test coverage, using the unit tests. They are easy to write, easy to maintain, and they're very fast and cheap to run. So we want to do the most coverage we can using a unit test. And these days, that's pretty good to do, even for UI stuff. But unit tests alone aren't enough, since they're only testing units and they aren't testing the integration between units. And you want to automate that part as well. So we also need service tests, for example, API tests, integration tests, and even UI tests. But the problem with UI tests, for example, is that they are much harder to create, they're harder to maintain, mainly because of we need actual data being there in the system, which you might need to reset, etc. So that's a bit harder to do, and they also take a bit longer to actually run. So we want to get to a proper right balance between all these types of tests in our system to get full coverage and get full confidence on the change we're making in an automated way. A particular project, what I really liked, we were using SpecFlow there. And I think SpecFlow is the .NET version, and there's also Cucumber, which is more known in the JavaScript world. But what it actually is that you get the ability to write your test scenarios in a natural language, English, for example. So that allows you to actually talk about those scenarios with the entire team, also the less technical persons, even your client. Everyone can understand what this scenario is telling them and if that's correct and what it should be doing. And that scenario then results into code that we can actually run to test the system. So for example, this method here, given as an authenticated user, actually comes from the given over here. So that translates into this particular function. And then we can use a tool called Selenium, for example, to drive the actual browser. So a browser is going to be spun up and we're going to navigate to a particular URL. We're going to find an element on the page. We're going to send a particular value to a text box, and eventually going to hit the login button and see if that all works. So that's a way to write the test on a pretty high level so everyone can understand what we're trying to test here and discuss if that is actually the right thing to do. All right, so I guess we still have 5 minutes left. I'm doing a bit quicker than I thought I was, but that's cool because that actually gives me a bit of time to dive a bit more into how we do database changes here in the build pipeline. Because doing database changes during your application deployment, and you probably want to have a zero downtime deployment, right? Being able to run your application at all times. So that means that at a certain point in time where you do your database migrations, you be in a situation where you have a new version of your database, but actually an old version of your application. So that means that they need to be backwards compatible with each other. So that also means that if you're going to do a change, you need to take that into account. You can't just rename a column, for example, because that would be a breaking change and that's not going to work. So you need to work your way around that. And in .NET, we have something called Entity Framework Migrations, which could be a really easy help to get that done. But the thing is that, as I said, we need to make sure that we are backwards compatible. Either the application needs to be backwards compatible, either the database needs to be backwards compatible to make this work. And that means that if you want to make a change, for example, a breaking change in the name of a column, that would require you to actually do a few migrations in different deployments to make that work. We need to make some database changes. We might need to make some code changes, and we might need some migrations to data, to change data or copy data, etc., to make that work again. So the benefit is that we can do zero downtime deployments, etc., but there's also a bit of downside to it, as it gets a bit harder to do the actual deployment and do the actual migrations here. So with that being said, that's kind of what I want to get across today. So thank you for joining me. And if you have any questions, then please join me afterwards in the chat. If you want to have questions after that, then you can always reach out to me via Twitter or LinkedIn or whatever. All is fine with me. So thank you for watching and have a nice conference.
Thank you, Erwin. We have a question from Lucas. So the question is how to deal with vendor solution when you don't have a source. Vendor constantly sends patches, updates. Deployment is to Windows VM. How you would imagine deployment of already compiled solution?
All right, so that's deploying an application that you actually bought from a vendor, for example. Well, you could still be using the continuous delivery practices and patterns to actually do that. We've done that in the past as well. And like I showed in the deployment where I was using infrastructure as code stuff to create infrastructure on Azure, we can do kind of the same things with VMs as well. And we can also easily automate the configuration management inside of a VM, which would also contain the upgrades from that specific vendor software. So tooling like Puppet and Ansible, for example, could really help you out in that matter.
Okay, thank you. So while we are still waiting for more questions, I have talked with the founder of Build Stuff Conference, and we have a record number of listeners at the moment. So please, I have this cool shirt over here. I don't know if you can see it, Rock and Code. And, you know, this is kind of a difficult, strange, and uncertain situation that we are here in. So I would like all of you to show your participation and take your photo while you are watching the presentations till the end of this day. Please post to any social media that we could track you. So we will need you to hashtag BuildStuffConf. Then you can tag me so that we can track you, and we will send you this t-shirt to everyone, wherever you are, all over the world. So also for the first 20, we will add this mask. This has a Build Stuff logo on it. So, and if you could add also the location, so we would have a feeling that we are here from all around the world, and let's participate. So we have Erwin. We have one more question from Pavel. Okay, staging environment. How do you handle a database? Do you make migration, which is backward compatible? I think you already answered at the end of, but maybe you can elaborate.
Yeah, that's indeed what I tried to get across at the end. We might actually get back to that. So what indeed is that you need to make sure that your database and your application are able to work with each other. So that means that what I often do is deploy my database changes first, which means that my application needs to be backwards compatible with basically 2 versions of the database there. And so making changes gets a bit more complex, but at least allows you to continuously deploy whenever you want.